All right, well, today we're going to continue along in our discussion of integration. Prior to this point, in the last section, we looked at U substitution, and so we're going to continue along with that trend here, except now there's two types of functions that we've pretty much omitted in those first two sections, and that specifically was dealing with integrals involving exponential and logarithmic functions. So in practice, the derivatives, we know how the derivatives work. You take the derivative of an exponential function, e to the x, you're going to get pretty much exactly the same thing back. If you have e raised to another power, which is like the power is some function itself, then we have e to the u times u prime. That's the derivative. If we go in the reverse direction, it's actually kind of the same thing. So the integral of e to the u is equal to e to the u plus c. So we're going to go through some examples, so hopefully this all kind of connects and makes sense, but I do want to just kind of point that out to you briefly. Also, specifically when we deal with logarithms, as you see here in the notes, okay, down below, logarithms, if you remember when we were looking at integration, we specifically said that the exponent couldn't be a minus 1, and the reason why that was the case was because the u to the minus 1, when you integrate it, is actually where you get the logarithms from. So it's kind of its own special, unique little case. Okay. And again, like I said, we're going to go through a slew of examples here, so hopefully this will all make sense. All right, let's go ahead and jump into it. All right, so on this very first example, let's go ahead and just take a look at the integral of 3e to the 3x dx, okay? So again, I want you to follow the process that I'm laying out here. It's going to be very similar to what we did in the last section with the u substitution. So in this case, we're going to set the u equal to that guy, okay? So I'm going to let u equal 3x. So then du, the differential, is going to be 3. So I take the derivative of the 3x, which is just 3, and then I multiply it by my dx, that same variable, okay, the differential of that x. I want to get the dx by itself, so 1/3 du is equal to dx. Just divide both sides by 3, or multiply by 1/3 on both sides, and it's going to wipe that 3 out on the right. And so now as a result, what happens is I can convert this into integral 1/3 e to the u du. Okay? Now we can take the integral of this, because the integral of e to the u is just itself. So all I'm left with as a result is just going to be 1/3 e to the u plus c. Oh, I forgot that 3. That 3 sits out in front. See, there's a 3 right here, so I need to account for that. So I can pull the 3 out in front, and then I'm still left with the, I was wondering where that came from. So 3 times that. So as a result, this is the same thing as just e to the u plus c, okay? Which is equal to e to the 3x plus c, okay? Let me do another one. That one might have been a little... you probably heard a pause, and that pause was me looking and like, that's not what I have written in my notes. That happens. All right, let's do this one. 1600 e to the 0.4 x dx. Okay. So I'm going to let u equal 0.4 x. So then du is equal to 0.4 dx. And then I'm just going to do 1 over 0.4 times du is equal to dx, which, by the way, this is the same thing as 5/2 dx. du here. du equals dx. Okay, so now we can make the conversion. I've got my 1600. That can be jumped out in front as a multiplier, or jumped out, I guess, pulled out in front, right? we're going to have 5 halves du, so 5 halves times e to the u du. And we can do the 5 halves times the 16. That's just going to be 4,000. The integral of e to the u du, which is equal to 4,000 e to the 0.4x plus c. Okay. All right. Let's go to the next one. On this next one, I've got the integral of 4 over e to the 1 minus 2x dx. Okay, so on this one, my initial suggestion right off the bat, I would highly suggest, well, I guess there's 2 different ways to do this. I'll do both ways so you can kind of see how this works. Okay. I am going to let, so this is way number 1. Let u equal 1 minus 2x, okay? So as a result, I'm going to get du is equal to a minus 2 dx, okay? Which means that minus 1/2 du is equal to dx. The minus 1/2 comes from that minus 2. I just divide by a minus 2. So that's where the minus 1/2 comes from. Okay. So as a result, this thing turns into the 4, which that comes along for the ride. It's just multiplying by the integral of 1 over e to the u d. See, I'm making mistakes here left and right. I need to have that minus 1/2 in there as well. Minus 1/2 times 1 over e to the u du, which is equal to 4 times a minus 1/2 is just going to be a minus 2. Then I'm integrating. This actually is the same thing as e to the minus u because that u is in the denominator. Du. And the integral of this is just going to be since there's a minus on there, it's going to undo the minus there. So this is going to be 2 e to the u plus c. E to the minus u, I should say, plus c. This way might not be the easiest way. The other way is probably a little bit easier. I should have started with that one first, but in any case. So then this is going to turn into 2 over e to the 1 minus 2x plus c. Let's do the other way, because you're probably like, dude, where'd you get all this stuff? The other way might just be a little bit easier right off the bat. In fact, if you go here, we're going to change this right up here to a minus 1 minus 2x. You can do that. So remember, if something is in the denominator, you can just slap a negative on it, and it's going to bring it up to the numerator. So that's literally what I just did here, okay? You throw a negative out in front of that entire polynomial. So this thing is the same as 4 e to the, you can actually distribute this if you want, or you could just leave it. I'm actually going to distribute it because it makes sense. The minus 2x is going to turn this into a plus 2x, and the minus 1 is going to turn this into a minus 1. So this is the exponent, and then we're going to get this. This way is probably the easier way. I would probably just go this route instead of the one that was a little convoluted up top. So let u equal, we're going to do 2x minus 1. du is going to equal 2 dx. And then I'm going to just do 1/2 du is equal to dx here. So as a result, this thing converts into a 4 times 1/2 times integral e to the u du. And you don't have to mess with the minus signs anymore. They all go away. So here you're going to get 2 integral e to the u du. And again, the integral of just e to the u is itself. So this is 2 e to the u plus c, which in this case is 2 e to the 2x minus 1 plus c. Okay. All right. There it is. How about them apples? All right, let's do another one. Again, I just want to run through some examples here because it's just really helpful to have as many kind of in your back pocket. Okay. All right, so on this one, we're going to do u substitution again. And in this case, you're probably going to see that something interesting happens. So I'm going to let u equal, again, you can kind of see where this is going. If I've got an 8 here as an exponent and then a 7, then I'm in pretty good shape with the u substitution. So I'm going to let this equal the one with the bigger exponent. And then if I do the differential on both sides, I get 8x to the 7th dx. And notice this whole thing right here is literally just right there. Okay, so I'm just going to leave this as is. So this thing pretty much converts into 1 over u du. Another way that you might see this written, just for reference, so if you see this in the textbook or online on homework questions, you may see it written as the integral of du over u. Okay, these are two equivalent expressions, and both are pretty commonly used. And so if you see it written like this, which, in fact, I think in the next problem we'll have a dx in the numerator, you'll see. But this thing actually is literally just the natural log of the absolute of u plus c. Okay? And then we can go back and redo our substitution here. So this is going to become x to the 8th minus 1 plus c. Many of these problems, if I'm being honest, they work out kind of nicely, and that's intentional. When we get to the tail end of chapter 13, which I think is chapter 13, section 6, we're going to do a process. It's the very last section of the course, actually. We're going to do a process called integration by parts, and so that will probably involve a little bit more complex, a more complex algorithm to go about solving these integrals. So you'll see when we get there. It'll be it's a fun time. Integration by parts is super handy for more complex integrals, and you can also do it with easy ones too. So, all right, let's do this. Dx over 4x plus 1. Okay, so I'm going to do the exact same thing. I'm going to let u equal 4x plus 1. And now I do my differential. Du is going to equal 4 dx. Okay, it's just the derivative again. And then I'm going to bring the 4 to the other side by dividing by 4. Okay. So now, as a result, we can go ahead and make this substitution. So I'm going to have 1/4. Again, you can put the 1/4 on the outside or the inside. It really doesn't matter. It's just a constant term. So the integral really isn't going to hit it no matter what. You can just pull it out. And then you're going to be left with du over u, which is pretty much what we said previously. So this is going to be 1/4 times the integral, or the antiderivative of that, which is going to be the natural log absolute u plus c, which in this case is 1/4 natural log. All right, so we got 1/4 natural log absolute of 4x plus 1 plus c. So there's our solution. Okay, let's do, let's see, do I got some more? Of course, why wouldn't I have more? I always have more. Let's do this one. Integral, whoops, I'm on my eraser. There we go. Integral of 4x cubed plus 2x all over x to the 4th plus x squared dx. Okay. So in a similar sense here, we're going to, again, kind of notice, you can kind of glance at it and see. Here I've got x to the 4th and x squared, and the derivatives of each of those respectively is pretty much just what's in the numerator. So right off the bat, you can kind of tell where this is going. So x to the 4th plus 2x, whoops, sorry, x squared. Making all kinds of mistakes today. X squared. So du is going to equal 4x cubed plus 2x dx. All right, so now this thing is going to convert. So you'll notice that the du is perfectly equal to what's in the numerator times the dx. So it's literally just du over u in this case. And that right there is just going to be the natural log of the absolute value of u plus c, which is the natural log of the original u function, plus x squared plus c. Okay. All right. Yeah, so I do want to point something out really quick, and that is that you can actually go about solving a lot of these on Wolfram Alpha. I probably shouldn't have told you that, but I'm going to anyway because, you know, it's a tool and I'm all about sharing information, and if it's going to be helpful to like going through and solving these problems, then why deprive yourself of something that's going to be beneficial to you? So you can actually use the math input here if you want, and you'll see the integral symbol. So this is different. This is a different symbol. We're going to get to that in chapter 13, which is the definite integral, but the indefinite integral, which is exactly what we want. So if, say, for example, I did, well, that previous problem, right? So let's look at, where was it? Where am I at? Oh, yeah, okay. So we got 4x. I'm going to put this in brackets. 4x to the 3 plus 2x divided by, there we go, x to the 4th plus x squared, oops, plus x to the 2, okay? And this is dx, okay? So if I hit enter, it'll think for a second, and oh wow, you're gonna get a really complicated problem here. I wonder what this should be. Oh, this is an alternate form. Okay, here. So this right here is your solution as well. They gave you kind of a different form up here, and I'm not exactly sure what they're doing here, but if you look down below, you can sometimes find alternate forms, assuming x is positive, which in this case we are because it's the stuff that's inside the logarithm. In this case, it would just be that. So you might just have to scroll down and kind of see some different potential solutions, and you can see there's all kinds of crazy stuff down here. But yeah, there it is. So FYI, a cool way of solving it. If you try putting this into the homework, you're probably going to get it wrong. I'm just going to tell you flat out. I don't think WebAssign actually will be able to recognize that as being, you know, a legitimate solution based upon, you know, the fact that we are assuming x is a positive value. Okay, let's go ahead and do a little bit more challenging one. And I do want to try to do this by hand, just purely because, my opinion, I feel like doing stuff by hand is really good for just kind of solidifying the concepts mentally. And so I just don't want to deprive you of that. So let's go ahead and do this. This is question, it's a question from the textbook. Let me just go ahead and read it. I just want to make sure I get this correct. So this is, what is it? Blood pressure in the aorta. Ooh. So if anyone's going into nursing and is going to study this, this is kind of a cool little factoid here. The rate at which blood pressure decreases in the aorta of a normal adult after a heartbeat is given by this. So we've got dp dt. dp dt is equal to a minus 46.645 e to the minus 0.491 t. Okay, So we've got our derivative, the rate of change, okay? T is time in seconds. So part A is asking what function describes the blood pressure in the aorta if P equals 95 when T equals 0. So what they're doing is they're kind of setting it up where they're giving you some initial conditions so that you can determine what that constant term would ultimately be solved for. So you can include it in your function. And so let me just write some information here. We know T is seconds. We know P is pressure. P is pressure. Okay. So that means that if I do dP, this is equal to minus 46.645 e to the minus 0.491 t dt. And I can take the integral of both sides. Minus 46.6. I know I'm writing this all out a bunch. Let me make sure I got that decimal in there. It's somehow escaped me. E minus 0.491 dt. I know that this is going to turn into a P right here. And so I just kind of have to work with that. Oop, there's a T here. I forgot that. Okay, there we go. All right, so in this case, we can do our u substitution. So we're going to let u equal whatever the exponent is. In this case, it's minus 0.491 t. du is going to equal minus 0.491 dt. And then I can just divide through. So 1 over minus 0.491 du is equal to dt. And now we can make all of our substitutions. So I know on the left, this is going to equal P. I don't have to mess with that. There's no substitution necessary. Then I've got a minus 46 point... That decimal place is just hiding. It's eluding me. 0.645 times 1 over minus 0.491 integral e to the u du. Okay? So P is equal to whatever this is. So this is one of those situations where you can go into Wolfram Alpha and plug it in, solve for it. It's actually pretty cool what this works out to being. It's literally just 95. So crazy. E to the u plus c is going to be our solution here, and then we just go back and resubstitute for our u value. So P is going to equal 95. E to the u is minus 0.491 t plus c. Now this is the important part, okay? Because they gave us the initial conditions. So they said that in this case, what function describes the blood pressure in the aorta if P equals 95? Okay, so we do 95, which is our P value. We're setting that equal to P. When T is 0, well, notice what happens. When T is 0 right down here, this whole thing just turns into 1, right? Or in this case, it's actually 95 because this e to the 0 is just 1, so this turns into 95 plus c. And if you cancel, you subtract the 95 over, you're going to find that c is equal to 0, okay? So that means that our actual solution, which I'm going to mark in yellow here, okay, the actual solution is going to be P. Let me erase this. P is equal to 95 e to the minus 0.491 t. That's it. That's our solution, okay? This whole thing right here. All right, so then the final question, part B, there was a part B on here, is what is the blood pressure 0.1 seconds after a heartbeat? All right, so they give us the known case, and then we have to figure out what the unknown is. So We don't know what the value of P is. Here they give us the time period, so minus 0.491 times 0.1. And in this case, you can literally sub that into Wolfram alpha. I'm not going to do that. I'll assume you know how to do that. So here we're going to do, this is going to be 90.45. Okay, so that's our solution. And they don't include units in here, so I'm not exactly sure what the blood pressure units are. Just that maybe it's just a value. I don't know. But those of you who are nurses can let me know of my ignorance, I guess. But yeah, so anyway, that's kind of a practical, realistic example of how something like this would work. But I'm going to leave it at that. And if you have any questions, feel free to let me know. But I hope you have a great day.